Hey guys, I created this video just to help you start problem number 1 if you're having trouble. I'm not going to finish it, so I'm going to do part A and some of part B, but other than that, I want you to do D and E for sure on your own, or you can ask me for help in class, but I'm just going to help you get started with this. So we have the bacteria problem for problem number 1. And I don't have the figure on there, so just go ahead and ignore that. But anyways, it says bacteria in a lab culture grow in such a way that the instantaneous rate of change of bacteria is directly proportional to the number of bacteria present. So although that first sentence doesn't really give me numbers and a whole lot of things, it does give me the fact that I have an instantaneous rate of change of bacteria. So that's something for me to know and is important. And it tells me that the instantaneous rate of change of bacteria is directly proportional to the number of bacteria present. So that right there, directly proportional, if you remember from class, or if I go back to this slide right here, K right here is the constant or proportionality, or I told you in class it is also, in some words will say, or in some word problems it will say directly proportional. Then you know that you're going to have a K in your differential equation. So far that's what this is, directly proportional. There's my K, and I know that it's directly proportional to the number of bacteria present. So in the part A, it says write a differential equation that expresses the relationship, then separate the variables and integrate the equation, solving for the number of bacteria as a function of time. So I don't really know though, if I just had only that, I don't really know though right now, what is time? Is it minutes, hours, seconds, I'm not sure. Or even in the last problem, or yesterday's problem that we did, it was years. So it doesn't really quite tell us there. But if you look in part B, sometimes you kind of have to explore and venture out to other parts of the problems to know what you are dealing with. So in part B, if I read that, it says, suppose that initially there are 5 million bacteria. 3 hours later, the number has grown to 7 million. Well, right there I know, okay, I'm in hours, and the bacteria is growing by millions. So I'm going to go over here to this blank slide, and that tells me that I'm going to let B equal the number of millions of bacteria, or you could put it as the number of bacteria, but make sure that you have somewhere in there like parentheses millions, because you need to know that the number that you're showing represents millions. And we also know that T is the number of hours. Okay, so that all came from part B. If you see again right here, the first sentence has 5 million bacteria, and then the second part tells me 3 hours later. So that's how I knew what my variables were going to be. Okay, so then going back to part A, whoops, wrong slide. Going back to part A, so I'm going to go ahead and say A. It says write a differential equation that expresses the relationship. So my differential equation would be dB over dt. So there's my derivative of B with respect to time, where B is the number of bacteria in millions, equals, and here's where that first part comes in handy. So right here, remember it said that it grows in such a way that the instantaneous rate of change of bacteria is directly proportional to the number of bacteria present. So again, the instantaneous rate of change, that's what dB dt is directly proportional, there's K, to the bacteria present. All right? And I keep clicking on wrong slide, sorry. The next part, so that right there is my differential equation that expresses the relationship. And now the second part of part A says separate the variables and integrate the equation. So again, separating the variables, I want b's on one side and I want t's on the other. So dividing and multiplying, I would come up with db over b equals k times dt. And integrating, I would have, db over b equals k dt, which means that, and sorry it's taking long, it's kind of hard to type all this, but bear with me. So just like the last problem, or the first problem that we did, if you remember, we had dp over p when we integrated. It works the same way. So db over b is ln of, not p, of b equals, and the integral of kt, or k dt, is kt plus c. All right, remember that this is just, k is just a constant. All right, and like the other problems, how do we get rid of ln, or what's the inverse operation? And hopefully we're all thinking that we have to raise both sides to e, or exponentiate them. So I have b equals e to the kt plus c. And using the trick from last time, we know that b equals c, because remember this would become e to the c, and then e to the c becomes big C because it's just a constant, times, sorry, I don't know why I put that, times e to the kt. Okay, so this is my general solution right now, and it is, I solve for the number of bacteria as a function of time, and it is my general solution. So let me put that, general solution. Okay, so there's part A. All right, now part B, let's go back one slide. Part B says, suppose that initially there are 5 million bacteria. 3 hours later, the number has grown to 7 million. Write the particular equation that expresses the number of millions of bacteria as a function of the number of hours. So now I'm trying to get rid of C and I'm trying to get rid of K. I want to actually replace those with numbers. So right here, this first part, there's my initial condition. Suppose that there are initially 5 million bacteria. Well, I don't really need to do much solving, because if we remember from here, it says when I'm given y equals c e to the kt, we know that c is the initial value. So I'm going to go ahead and say b equals 5e to the kt. There is my initial condition. And if you wanted to check and make sure that I was right, you can substitute 0 for t, and then b would be 5 from the initial value, because when it first started, the time was 0 hours and bacteria was 5 million. So you can check that if you want, but I'm just going to use that from here, knowing that C is my initial value. Okay. Secondly, the second part of it says 3 hours later, the number has grown to 7 million. So that's telling me that when time is 3, there's 3 hours, the bacteria is 7 million. Okay. So all I'm going to do is substitute that into my equation. So 7 equals 5e to the k times 3, because there's time. Whoops. Let's try that again. Times 3, because there's time. And once you do all your math and all that good fun stuff, you come up with k equals 1/3 times ln of 7 over 5. So then your final particular solution is b equals 5e to the 0.112, and there's a whole bunch of decimals after that, but I'm going to round it t. And that right there is my particular, I don't want it to be small, particular solution. Okay? So now from here you should be able to solve D and E. If you do have questions, again, please ask. Pause the video at any time. Ask me what I did, how I did it. But I'm hoping that seeing this video along with the other couple videos and practice problems, you can try and attempt to do and write your own differential equation for number 3. Okay? All right.